Hello, we are here to discuss some common discrete distributions. Really, we're just going to discuss two discrete distributions, the binomial distribution and the Poisson distribution. But let's begin with an example. This is not from bioinformatics or biology. It is from basketball, and in particular, my favorite NBA player ever, Ray Allen. He is retired. He is a Hall of Famer. And Ray Allen had a 40% three-point percentage in his career. So the statement is, we suppose he attempts 8 three-point shots. What is the probability he makes the first 5 and misses the last 3? Now, in order to answer this, we need some terminology, which we will explore more in the next module. However, I can introduce it here. We have events, A and B, and some sample space S. We say A and B are independent, and this is a statistical term here, provided the occurrence of one of them does not affect the probability of the occurrence of the other. So that's kind of in words. One way to say this mathematically is as follows. The probability of A intersect B, this means A occurs and B occurs, is just the product. Probability of A times probability of B. Well, how does this have anything to do with the question? Well, let's suppose we call success on a single shot is that Ray Allen makes the 3, and failure, well, that he misses. And I will denote success by an S and failure by an F. Now, we know some things here. We know based on his three-point percentage, we know the probability of S is 0.4. And there's only 2 possibilities here. Either he makes the three-pointer or misses. So the probability of failure would be 1 minus this probability of success, which is 0.6. That's just for one shot. Now, we have 8 three-point shots, and we have a specific order. So what is given in this problem, the event here is we have 1, 2, 3, 4, 5, 1, 2, 3. There are multiple ands here. So this is really, he makes the first and, makes the second and, makes the third and, makes the fourth and, makes the fifth and, misses the sixth, etc. Misses the seventh, misses the eighth. There are ands throughout. Now, we can assume here that, say, making the first does not affect the probability of making the second, etc. So what we would do here is just multiply. So the probability, the answer here, we have 0.4. This is the probability of success, and there's 5 of them. And then we have 0.6, and there are 3 of these. You can use R or some other calculator to calculate this. This is approximately 0.00. We have 2212. All right, now here's a totally different question. What is the probability that Ray Allen makes 5 of the 8 three-pointers? If we go back to letter A, you see this is one possibility. It would be you make the first 5 and miss the next 3, but it's not the only possibility. So we're still taking, or Ray Allen is still taking 1, 2, 3, 4, 5, 6, 7, 8 attempts. And all we know is that 1, 2, 3, 4, 5 of them will be S's and 3 will be F's. Maybe it's these 5 or really any other possible 5s. So we will still have this part appearing. Maybe I'll just copy this and paste. This part is the probability of one specific pattern of 5 S's and 3 F's. But then we have to multiply this by, well, 8, choose 5. Now let me do this underneath in black, and choose K. Well, it's read like this, and choose K. And in R, the code is this, choose NK. What this is the number of ways to select K objects out of N. So in this example, 8 choose 5, say it's 1, 2, 3, 4, 5. There are the 5 places that I would put an S. Those would be the 5 times Ray Allen made the shot, and the other 3 you could fill in with an F. Those would be the times he misses. So the total probability is exactly this, which, once again, you can, maybe I will even show this in R. So if I enter, choose 8, this is 8 choose 5 times this 0.4 to the 5th, 0.6 cubed. Well, here is this probability. It's approximately, well, I'll just keep all of the decimals. 1, 2, 3, 8, 6, 3. Now, this is our very first example of a binomial random variable. The definition, the probability mass function of a binomial random variable x is, well, f of x, and choose x. That's the number of ways to select x objects out of n. P to the x, 1 minus p to the n minus x. And here the support goes from 0 through n integers. So in this, it's important to understand that n is one of our parameters. This is, say, a positive integer. And the other parameter, p, is a probability. And as you see in this important remark, this is discrete. Support, in fact, has n plus 1 numbers in it. It's 0 through n integers. Okay, very nice. Now, how do you know if a random variable is a binomial random variable? Well, what you have is exactly like the first example we started with. We have some experiment or trial performed exactly the same way n times. Each of the n trials has only 2 outcomes. One of them we call a success. One of them we call a failure. And this is called a Bernoulli trial. The n trials are independent. This is the statistical word I was mentioning. The probability of success is denoted P, and it's the same for every single trial. And therefore, the probability of failure is 1 minus P. Finally, our random variable is the number of successes in the n trials. So all of this is exactly what we just had in our first example. Now, here's another one that comes from biology. If 30% of nucleotides in the human DNA are adenine, let X denote the number of adenine bases in 3 randomly selected nucleotide bases on the DNA. We want to calculate the probability there are at least 2 adenines. Okay, first of all, you'll notice that X is distributed as binomial, where we have n equals 3. Maybe I'll write that, n equals 3. And the success here is that we get an adenine, and then failure would be we get anything else. So P equals 0.3. What we want is we want the probability that capital X is greater than or equal to 2. So there's a few ways we could do this. One would be to just take, well, first of all, let's write the support, because this will actually help us. You could have 0 adenines, 1 adenine, 2 adenines, or 3 adenines. So what we could calculate here is we could calculate f of 2 plus f of 3. This is discrete, and so the probability that I'll do it this way. Capital X equals X is little f of X. That's one of the nice things about discrete random variables. Well, so we have f of 2 is 3 choose 2, and then we have the probability of success to the 2. We have probability of failure to the 1. And then plus, we have 3 choose 3, the probability of success to the 3, probability of failure to the 0. We get 0.216. So here's the answer. Now, is this the only way you could do it? No, there are other ways. Recall the cumulative distribution function. We saw this in our last exercises. This is the probability that capital X is less than or equal to little x. Now, if you stare at the support here, in this example, if you want the probability that capital X is greater than or equal to 2, it would be 1 minus, well, I'll do it this way. So we're wanting the probability here. It's 1 minus the probability that X is less than 2. This is 1 minus the probability that X is less than or equal to 1. And you could write this as 1 minus f of 1. This is something that you can have R calculate, for instance. Well, similarly, this way, this is just a remark. And we will get to the R later. But we have the answer here, 0.216. All right, now some properties. If you have a binomial random variable, there are these two parameters, n and p. The mean is n times p here, and the variance is n times p times 1 minus p. Well, let's do an example where we use these formulas and also think about here, this is linear transformation of a binomial random variable. Okay, so the first example, we can just directly apply the formulas above, where we are working with the exact same binomial random variable of the last example. We had n is 3, p is 0.3. So for number 1, the expected value of x, well, this is just 3 times 0.3, which is 0.9. And then the variance of x, well, we have 3 times 0.3 times 0.7. Well, this is 0.9 times 0.7, which will be 0.63. Next question. Well, we have formulas from the last module to calculate expected value and variance when we have this linear transformation of a random variable. And so the expected value of y, this is 2 times the expected value of x plus 1. And so we get 2 times 0.9 is 1.8 plus 1. This is 2.8. When we go to calculate the variance of y, this is 2 squared times the variance of x. And in this case, we get 4 times 0.63, which is 2.52. Number 3, is y a binomial random variable? Why or why not? Whoa, how are we supposed to answer this? Well, we have to go back. Really, the key to answering this is to realize that every binomial random variable, the support will start at 0 and then contain 1, 2, 3, 4, etc., all the way up to some number n. So we can answer this just by looking at the support. The support of y, well, the support of x is 0, 1, 2, 3. So we would have 2 times 0 plus 1, which is 1. 2 times 1 plus 1, which is 3. 2 times 2 plus 1, which is 5. And 2 times 3 plus 1, which is 7. So we know the answer is no. This is not of the form 0, 1, 2, out to some n. And so the answer is no. This is how we can answer that. So in general, if you take some variable, random variable distributed some way, and you take a linear transformation of that random variable, it will not have the same distribution, not always. And we see that in this very first example. Now, the next discrete distribution I want to talk about is the Poisson distribution. And this one has support, well, all non-negative integers starting with 0 and marching forward. This is often used to model the number of times an event or a change occurs in an interval of either time or space. This distribution comes up a lot in biology and bioinformatics. But some examples, well, the first two examples don't come from biology, but the number of typos on a printed page, the number of customers arriving at an ATM in, say, a 10-minute interval, or the number of mutations on a genetic sequence. Well, the probability mass function of a Poisson random variable, here we have one parameter, lambda, and lambda should be positive, is given as follows. F of x is lambda to the x divided by x factorial, and then times e to the minus lambda. Now, we have seen this distribution before without knowing what it was called. If you recall, in our extra practice module 3, we had a discrete random variable x. We were given this probability mass function with the support non-negative integers. And if you look at this and you stare at this, you notice that this particular x is distributed as, well, it's Poisson, where lambda equals 3. And we did some things with this. We calculated some probabilities. We also, using series, verified that, in fact, this is a probability mass function. Okay, some remarks here. The mean and variance for Poisson distribution are all the same. It is both just lambda. The expected value is lambda, and the variance is also lambda. What I want to do is spend a few moments talking about distributions in R, and then I will show you how you can calculate this. This particular quantity we calculated on our worksheet, but I'll show you how you could use R to do so. So in R, most major distributions are built in. It's one of the wonderful things about using R. Every distribution has a root name, but then you can put a prefix letter in front, and from that prefix you get 4 different functions. Prefix P gives you the cumulative distribution function. Prefix D, well, in the discrete world, this is probability mass function. For continuous random variables, it's probability density function. Prefix Q, this is a quantile function. We will talk more about that in later modules. And then prefix R is for a random variable with that distribution. So we use this to sample from the distribution, and we will be doing that later this module. Let's end with this example. We have a Poisson random variable x, where lambda equals 3, and calculate the probability that x is bigger than or equal to 2. This ties into the remark I made earlier when we were looking at a binomial random variable. But now I'm actually going to work in R and I'm going to use the cumulative distribution function here. Okay, so let's talk about the math sum first. The probability that x is bigger than or equal to 2. This would be 1 minus the probability that x is less than 2. Now, we are in the discrete world, so less than versus less than or equal to, these are different. And that is an important difference in the discrete distributions or discrete random variables versus continuous. So we are in the discrete world right now. Okay, so this is equal to 1 minus the probability that x is less than or equal to 1, which is 1 minus capital F of 1. Now, what are we going to do in R? In R, we are using the P prefix. So this would be 1 minus P. Poisson, the X is 1, and the lambda is 3. So let's do this now. We type 1 minus, just like this, P Poisson 1, 3, and we get 0.800 equals 85, so I'll just say 9. If you go back and look at the worksheet where we calculated this without this built-in function from R, we had this exact same value. Well, this is all I have to say in this video. Thank you so much.